guys, I hope you like this format better. I try to do a little bit brighter, a little closer up, so you can see what's going on. There is nothing more fun than doing YouTube videos. I am actually going through a sort of rough period right now, and so this is helping a lot to just share something, share some knowledge. The main idea with doing YouTube for me is that I like the idea that adults get busy, and a lot of us have jobs that take up a lot of our time. And so when you go to learn something, you really want someone that's like into it, you know what I mean? And I'm no physicist, like I don't have a degree or anything like that. I just am a heating and air conditioning type of worker who had some experience with freon and fluids and pressures, things like that. And now I got into cosmology because I understood some of the interplay between like subcooled fluid or like supercritical or superheated fluid. Basically, tonight we're gonna talk about the Big Bang. We're gonna link it to phonons in the brain, and then there's even gonna be a little bit of a cognitive skill part. But not to scatter things too much, but just let's get to the Big Bang, right? When this happened, right, this singularity that blew off, you have to picture something as dense as iron, like you can't go through it. Only this is a quantum object. This thing is so collapsed that, like, when you say you can't go through it, that's like a big time understatement. And the other thing is masses. Just like if you put on a coat with a bunch of feathers and lay under a blanket, your body heat will build up. The singularity started off super hot when the Big Bang went off. This is what happened. In the first, like, microseconds, okay, it started to expand. And within a few seconds, you already had the components needed to make protons, okay? You had quarks and electrons that were floating around, all right? And if you don't know anything about that, it's just some basic quantum mechanics. The quarks are the ones that stay in threes, okay? With neutrons, usually, always actually, you'll have two down and up. So if you could think of a neutron as neutral, like in electricity, we'll tape a neutral to like a railing, you know what I mean? And that creates the circuit. But here with the neutron, just picture two down quarks anchored to the ground, let's call it, and then one pushing up. With the proton, right, which hydrogen, you only have a proton, that's all you have. But when you get to helium, you're going to have a neutron. So with the proton, you're going to have two up and a down. And you could think of that as connecting in a way to the neutron, which has the two down and an up. So the proton's got two up and a down, neutron's got two down and up. Inside, deep inside, you have quark and gluon, and there's an interplay between those two. Virtual phonons go back and forth, okay, just like light, literal light, quanta energy, right? This is quantized in mathematics. So in a proton, you have these three quarks, and you have the gluons, which hold them in as well, that produces the strong force. There's another force, the electroweak force on the other side of things, closer to the vacuum of space, that is fed from the W and Z boson and Higgs, which gives rest mass to mass. So like your electron has mass because it's in the Higgs field, electron field and a Higgs field. Similarly with all particles, that's how they get their mass. So this sombrero acts as that first anchor or first curvature in a way that keeps quarks there. So right after this happened, all right, this few microseconds go by, you've already got these quarks and electrons, and it's very hot, all right? It's in the trillions of degrees. But it dropped in trillions of degrees, and it went down to like 1 billion degrees. And what happened was it got so cool, and it had expanded enough that electrons were like, I'll hop onto that. So they hopped onto the proton, and now you started to have atoms, right? Well, about 400,000 years after the Big Bang, right? Atoms are good and bumping, all right? And photons now can move around because when you put things together, you created more room. So now photons can move how they want. Instead of just banging off electrons or electrons absorbing them because there was just so much turbulence at that time. Now, because there's more room, photons can move around. Space, who knows what size it was, but from the calculations, up to about between 1 and 6 billion years, you had a lot of star formation. And then stars were those first gas clouds that collapsed, and their fusion process is what creates the heavier and heavier elements. And then now you have denser chunks, that collapse. And then when you get into those realms, now you're talking, you could be making galaxies, because now you have all these star remnants that are all going to fall to center together. And that's what you're going to end up with, is galaxies. Where this ties in to mental health, good cognitive skills, that kind of thing, is, and this is ironic, but those virtual photons in the brain, like, we don't know that when you take in light, something happens, you see it, the electromagnetic force, you pick up light, you pick up sound waves, your brain tells your neurons in your brain tell your brain, we have experienced this. Well, once you have a memory in place, really, is that stored in the mass of the brain, or is that just more light, right? It's a memory of light in a way. So it really doesn't exist anywhere in time when you think about it, because it comes out of nowhere. Like, if I think a thought, a memory pops into place, that really is timeless, because it's going at light speed and it's getting to where it's being received instantly. So in a way, black holes and human minds are similar, because they're the only two places in the universe where causality is only observer independent to each observer. If I'm falling into a black hole, there's no way anyone outside of it can ever see it the way I'm going to see it. And if I have a memory, there's no way anyone can ever see it the way I'm going to see it. So human mind and black hole have some good connection there with that, especially with the energy content, the phonons, the virtual photons, the entanglement process of energy, perhaps mass and energy behaving the same, but they're nowhere near each other. One crucial point I wanted to get into is the little red dots. You'll see those a lot. You'd be scrolling through and you'll see, like, oh wow, astronomy, cool, and you look and it's like jades and these different red dots. Remember, as we look back in space, we're also looking back in time. So for instance, the Phoenix cluster is going like 400 million miles an hour, and it's like dipping, like leaving with the expansion, like a wind sail, right? But the version we're seeing of that is that old as well. So we're not seeing it now. We're seeing it, whatever it is, like 9 billion years ago, whatever it is, how far it is, I'm not sure exactly, offhand, but I believe it's at that sort of range. Like the Milky Way was created probably not too far after the Big Bang, because they've found stars, okay, in the Milky Way that are almost as old as the universe. So that wouldn't be happening unless those stars were created, shortly after the Big Bang. The main idea about the Big Bang is that that's what's going to help you understand the quantum mechanics. Because if you can understand that something is so dense and hot and packed with mass, and now as it begins to cool and expand, right, now things can move around, right? So now your quark and your electron field, rest masses, right, can move around. They can fall into each other, this kind of thing. So the formation of atomic nuclei, baryonic matter, fermions, just to give you a basic on that, a quark is a fermion, an electron is a fermion. It's also a lepton, but an electron is also a fermion. There's fermionic behavior and then bosonic. You have spins, so like a boson, a Higgs, a WZ boson, they have a spin of 1, all right? Whereas with your proton and your neutron, remember, you got quarks in there, so, and that's electricity. So there's a 1/3, 2/3 split the difference with those so that they come out right. And they also have color charge. So they can be blue, green, and red, which makes them white. And by being white, that's what makes them perfectly, you could call it ripe for the electron to hop on. The general relativity, really, that's the best. But where the general relativity can take you in your understanding of space is that when they talk about the shape of space, geodesics, curvature, what they're really saying is that one thing is meeting the other, and they have a content that they're worth. They have temperature, they have a direction, okay? And when things collide, they end up in spirals. And everything's moving at the speed of light unless it's slowed down. Because we know energy moves at the speed of light unless it's hindered in some way. Now, you can't move mass at the speed of light, because if you do, you release infinite energy, right? So there's a differential there, right? But you can move photons at the speed of light, which is why over time, as they travel through time, the vacuum of space is getting stretched out, and you're getting redshifted. Like when we look at the galaxy, or galaxies, we've even looked at the Milky Way, Andromeda, but when it's the best astronomers, Vera Rubin, Hubble, James Webb, Chandra, the best schools, when they look at space, they can tell the difference between flying at something and what the light looks like, blue shifted, and also in the trail behind them, the red shifted light. So the vacuum of space is expanding, and they believe it's happening at faster than the speed of light because light isn't keeping up with it. And where Einstein came in is that he brought the photoelectric effect, which, if you shine a laser at metal, okay, the electrons will get knocked off. And this is part of like how we have like solar panels and stuff. Like that's how they developed that technology. The photoelectric effect had everything to do with that. The equivalence principle, inertial mass, non-inertial mass, falling in from gravity. He's telling you that if you're flying up in a rocket ship and things are sticking to the floor, and when you pick something up, it falls to the floor, you don't know the difference between being moved and gravity. Similarly, if you're in the back of a car, you're driving forward, you're sticking to the seat, and the driver takes a turn, your body goes left into the curvature of the door, where the door and the seat mix, right? But that's just because your body's inertial and it's trying to go straight and see the car's turning. So the car's creating curvature and acceleration, and you're ending up in the 45-degree where the door and seat meet. The Earth, by all estimates, the Earth revolves around at 67,000 miles an hour. It revolves around one solar mass main source star we call the sun. It's full of fusion. It has spicules and granules on its surface. It is a gaseous plasma state with tons of photons and X-rays and every other harmful ray you could think coming out of it, because it's nuclear. That's what fusion is doing. It's releasing, and energy is always conserved. But we are falling around this star, and our planet got cooked up in a protoplanetary nebula. And what happens is stars, when they're new, they can cook up planets. And our planet got cooked up. And it's falling around the sun. But as it is, so you're in an elevator going down, you know what I mean? And then that star is also leaving the area at 500k miles per hour. So you picture that. Your Earth is revolving around your sun, and as it does, there goes the sun around the galaxy, right? Now consider at 1,000 miles an hour, you're being spun because you have the spin of the Earth as well, the rotation, okay? That's got a little torque to it, right? It's moving everything in a relativistic fashion, so nothing really knows it's moving because everything's moving. But if you think about it, as you're on this curved path around the sun, you're also being turned. So really, you're always being turned to center, and you're always being lifted. And that's what the equivalence principle really says to me. The last part of that, and this is huge, the violation of the parallel postulate. That is a simple one. What happens with that is, if you're on one side of a pool and I'm on the other side and we both have skateboards, we'll ride into the center and we'll end up at the bottom together. Our masses will actually stick together. Now, if you look at the shape of space around the Earth, it's shaped like a pool, isn't it? But it doesn't have any support, does it? And you're on a moving body that's spinning too, right? So even if the Earth were to go really, really super fast and throw you a little bit, you'd always be coming back down, wouldn't you? Because it would be throwing you on a curve, wouldn't it? So you can see how you can really never escape without force to get away. And the last part of this is time. There are world lines, like when you leave the ground in a rocket, you think you're shooting up straight, okay? But as this frame turns, you'll see this rocket start to curve like this on its way out. So from the time it started to the time it got to the furthest point, it's going to make a big arc because it's moving through time. The last point here to wrap this up for tonight is that those basics that I touched on regarding the Big Bang, subatomic particles that make up atoms, okay, because of course your baryonic matter, your hadron, your proton and neutron, that's going to give you your atom, okay, but you need what? It has to be cool enough, right, for everything to form a capsule. You have your weak force, your strong force, and your electromagnetic force, right? Magnetic fields, that's one we haven't even touched. Magnetic fields, there's an electric field and a magnetic field, and one acts on the other. Really, one cool thing with black holes, when you get to that level of acceleration and those kind of high densities like that, because when the star collapses and becomes a black hole, it's mad dense and perhaps hot, but it cools to absolute zero because particles can't move around. There's too much gravity, everything is too packed, so the thermal energy goes out the window. But that's on the inside. As these things eat and get bigger and their volume goes up, they get less dense. So they might actually get down to as less dense as like the air or like water. You know what I mean? Because it just depends on how much room you have, right? Well, these ultra massive black holes, like at the Phoenix cluster, like 100 billion solar masses, that density is probably less than air. Honestly, it's probably something along the lines of not quite like space, but somewhere in between space and a very light atmosphere. All right, because of the volume, the mass density, of course your thermal energy density goes out the window. All you have is your entropy, which represents itself right along the edge. They have something called the don't let this slip my mind, come on, the holographic effect. This is where this black hole, not only does it have Hawking radiation, but like a very low blue wavelength, like similar to sound, but it also bends light around the bottom and the top. So like when you look at it, you're seeing various parts of time all at the same time, all in one 2D picture. And if me and you were to get in a rocket, this is a trip. If we were to get it to a rocket and actually be able to get near one, which you can't because they're too far away. It would take lifetimes to get there. But let's say we could. From far away, you'd see a red shifted haze. It would look something like a star, okay, depending on if it was an AGN, if it's eating a lot of gas, there's a lot of photons, gases heat up and release light, da-da-da-da-da. But, you know, let's say, like, we were coming up on Sagittarius A. You'd see a red shifted haze around that thing. And as you went to go near it, you would detect motion, but you wouldn't understand your motion. But you'd already be moving toward the black hole. And you might make it around it a couple times. But by the time you got near to the event, if someone else was watching from the outside, it would look to them as if you froze at the edge and never went in, right? Time stops when you get to the event horizon. It's the end of time. Like, there's no more electromagnetic force, there's no more measurement, none of that stuff. It's like gone. Anyway, I hope you enjoyed this. We're gonna do more of these. These are gonna be fun. Like I said, I'm not an astronomer. I haven't been to school, but I have been to school a little bit. I know enough that I can tell you some stuff.